In this video, we continue with Unit 14 and we focus on the motion of charges that are inside a region where there is a magnetic field. So, as you know, when there is a charge moving in a region where there's a magnetic field, there is a force exerted on this charge. The force is, as we have seen previously, equal to the charge times the velocity, the cross product of the velocity and the magnetic field. So we already talked and said that this force is perpendicular to the velocity of the particle. So this implies that it cannot modify its speed, the magnitude of the velocity. It cannot modify it because the force is perpendicular to the velocity. What it can alter is the direction. Okay, it can only modify the direction of the velocity. And another thing interesting about this force that is perpendicular to the velocity is that it does not do work on particles. It cannot change the kinetic energy of particles because it cannot change the magnitude of the speed. It cannot change the magnitude. It can only change the direction. So let's to analyze what's going to be the type of movement we're going to get in this kind of in a particle that is moving inside a region of that has a magnetic field. We're going to explore different cases. Okay. In any case, in all of the cases, the force will not alter the speed, the magnitude, only the direction. Okay. So the first case, which is the simplest case, is when the velocity is parallel to the magnetic field. This is the simplest case. Because in this case, if this is so, you know, because you know a lot of cross product, that the cross product between two vectors that are parallel is 0. And hence, the force is 0 in this case. So the particle, the charged particle moving in a magnetic field with a speed that has the same direction or contrary, that is moving parallel to the field lines, does not feel any force. Okay, this is the simplest case. Then we're going to complicate things a bit further. Imagine another case. So in another case, the velocity is completely perpendicular to the magnetic field. Okay, this is another extreme case. So in this case, we're going to try to discuss it. So imagine you have a positive particle, charged particle, that is moving towards the right. Okay, that is the speed, the velocity, and there is a magnetic field in this area. So the magnetic field is going to go. It's going to go into the screen. So I'm going to plot it as x because it's vectors that are entering the screen. So I'm thinking of a region that has a uniform magnetic field. This is why I'm trying to plot these x with the same spacing, between them. And when I plot an x, it means that the magnetic field is entering is going through the screen, is going into the screen. If I had plotted points like this is a magnetic field that is going out of the screen. Okay, this is going out of the screen. But we are in this case. So in this case, if the particle has a positive charge, we can calculate what is going to be the direction of the force. Okay, so to do that, we have to apply the rule of the right hand, and we get on our index the velocity pointing towards the right. On our middle finger, it's the magnetic field, which points into the screen. So our thumb is left. Sorry, it's left pointing upwards. So this is the force at this instant. Okay, it has this direction. If the charge were negative, the force would have the same direction, but opposite. It would go down, okay, instead of up. So here we have this particle, and as there is this force, in the next instant, this is not going to change the magnitude of the velocity, but it's going to change the direction. So in the next instant, the particle is going to be in this place, okay? And the velocity will have changed not its magnitude, but its direction, okay? So if you do again this calculation, you will end up showing that the force will have this other direction, and then this will change the path, and it will always point toward, it will always be perpendicular, and it won't change the velocity. So this is going to provide a normal acceleration. It's because if you remember the second of Newton's law, okay, then here, if there is only the magnetic field, as this field, this magnetic force is perpendicular to the speed, to the velocity, then there can only be a normal acceleration. Okay, it's always perpendicular to the path. Okay, so this ends up providing you a circular path where the velocity, the speed, the magnitude of the speed is constant, and you're just changing the direction, providing you with this circular path. I think we can see it better in the next slide, where you can have it picture. You have a nicer picture. Okay, so this is going to be the path that the particle is going to undergo, and then once it gets here, it begins again. So it's just moving in circles. This is with a constant speed. So this is a uniform circular motion, okay? Then, knowing that this is a uniform circular motion, we can derive certain parameters, know what these parameters of this circular motion are going to be. The first thing we could do is calculate the magnitude of the force. As we know that it's perpendicular, the magnitude of the force that we can just state as F, or here like the modulus of F, is going to be Q times V times B. And this is so because both velocity and the magnetic field are perpendicular, okay? So this has to be equal to, this is Newton's second law, this has to be equal to the mass times the acceleration. And this acceleration, as I was telling you before, is normal. It's a normal acceleration. If you remember from cinematics, a normal acceleration can be explained, it can be expanded. It's related to the speed of the movement by this. So the normal acceleration is the square of the velocity divided by the radius. Okay. So from here, it's easy to derive what the radius is going to be. Okay. So the radius is going to be equal. We just take away one of the velocities at each side of the equation, and then we can say that the radius is going to be equal to the mass times the velocity divided by the amount of charge and the magnitude. Okay, remember that this is just in this case, okay, when they are both perpendicular. We can also derive different other parameters, because we can this is a uniform circular motion, so we can derive, for instance, what is the angular frequency for this motion. If you remember, the angular frequency was the velocity divided by the radius in these uniform circular motions. So this, if you bring this here and you put v divided by r, this is going to be equal to qb divided by m. Okay, so this is going to be the frequency, the angular frequency, which is called the cyclotron frequency. And from here, as we know that this is 2 pi, the frequency in Earth, we can say that the frequency in Earth is going to be 1 divided by 2 pi times qb divided by m. Okay, and this, as we know that the period of this motion is 1 divided by this frequency, this period, what is called the cyclotron period, is going to be equal to 2 pi times the mass of the particle that is moving through this uniform circular motion divided by q times b. Okay, which is quite interesting. It does not depend on the actual speed of the particle, but on the relation between the mass and the charge of the particle and the intensity of the magnetic field. Okay, so now we've seen two cases. The simplest one, in which the velocity is completely parallel to the magnetic field, in which case there is no force exerted on the particle, and this other extreme case in which the velocity is completely perpendicular to the magnetic field, in which case what we have is a uniform circular motion where you can derive several parameters as the radius of the circular orbit, or the cyclotron period, or the cyclotron frequency. Okay, so now we're going to look at the third and most common case, in which the magnetic field is neither completely perpendicular, neither completely parallel to the velocity. In this case, what we're going to do is say that the velocity, the whole velocity, can be decomposed in a part that is completely parallel to the magnetic field, and another part that is completely perpendicular to the magnetic field. So the part that is completely parallel, as this part, the cross product between the parallel part and the magnetic field is 0, then this component is not modified in any, neither in speed nor in direction. Okay, and the other component, this is different from 0. And we've already seen what this perpendicular component what is going to happen to this perpendicular component. As we've seen that it's going to follow a uniform circular motion for this component. So then you have to go back to the composition of both, and then what you're going to have is an helical motion. So some helix, some spiral. Okay, so what you have, if this is the magnetic field represented by these blue lines, okay, it's a uniform magnetic field, and you have a particle like this one with a charge that is moving with a speed that is not completely perpendicular nor completely parallel. The parallel part is going to make the particle move towards the right, because that was the original movement. And the other part is going to make the particle go round and round in circles in this other component in a plane that is perpendicular to the magnetic field. And if you compose both motions, this is what you get is an helical motion.